Good morning, guys. Today we're going to learn about acceleration, and I'm going to talk over some notes that I've written, and then we're going to look at the formula. But first, I want you to watch this YouTube video. It kind of goes back and explains a little bit about position, and then velocity and acceleration, and how it all ties into each other. So we're going to watch this first, and then I'll come back to the notes.
Did you know detergent leaves behind bacteria? New Clorox fabric sanitizer kills bacteria between washes.
Hey, it's Professor Dave. Let's discuss position, velocity, and acceleration.
He knows a lot about the science stuff. Professor Dave explains.
In physics, we will often be asking questions like, where is an object? Which way is it moving? And how fast? To discuss the answers to these questions, we will frequently utilize the concepts of position, velocity, and acceleration. So before we go any further, let's define these terms. Position is simple. It's just where an object is in space. Usually this is discussed with some kind of reference point or axes in mind, and we might express the position of an object as being some distance from this reference point in meters. Velocity is the change in position over time. So if this object travels 5 meters in 5 seconds, it is traveling at a velocity of 1 meter per second. And acceleration is the change in velocity over time. So if this object starts at a standstill and over 5 seconds gradually speeds up to 5 meters per second, then it is accelerating at 1 meter per second, or 1 meter per second squared. So that's how we define position, velocity, and acceleration. Now let's discuss each of these in more depth. When we talk about position, we could discuss distance or we could discuss displacement. The difference here is that distance is a scalar, while displacement is a vector. Let's say you and your friend get dropped off by the school bus at this intersection, and your house is here. Your friend begins to walk down the street and up the driveway like a normal person. But you find yourself so overcome with excitement to play video games that you decide to plow through the yard in a straight line to the door. Your friend has to walk 20 meters down the street and 7 meters up the driveway for a total of 27 meters. So, using the Pythagorean theorem, we find that you only had to walk about 21.2 meters, and you probably got there a little sooner. What we can say is that you walked different distances, which are represented by these scalar values, but you both had the same displacement because you ended up in the same spot at the front door. This vector, which follows the straight line path, is the displacement vector for both of you, and we can report your position with x and y coordinates like this, 20, 7. Or we could report the magnitude of the displacement vector, which will be equal to the shorter distance you traveled, and calculate the angle off the horizontal using trig functions if we desire, in order to report the direction of the vector. Next, let's look at velocity, which is the rate of change in position. Most people assume that the words speed and velocity are synonyms, and in everyday language they are. But the difference in physics is that speed is a scalar and velocity is a vector. If a group of kids are playing hide and seek and they all run away from the seeker in different directions, it is possible that they all run at the same speed because speed only has magnitude and no direction. So they could all run at a speed of 3 meters per second if they are quick little devils. But each kid would have a unique velocity vector that has a magnitude of 3, but also describes the direction of motion, most likely using the seeker standing still as the point of origin. Velocity vectors will be extremely important as we move forward with kinematics, where we will study the motion of objects. In general, average speed can be calculated by taking the distance traveled by an object and dividing by the time it took to do so. So if you walk 85 meters in 46 seconds, you are walking at an average speed of 1.85 meters per second. To find average velocity, you can do the same, but you would have to divide displacement by time. Lastly, we have acceleration, which is the rate of change in velocity. This is always a vector because acceleration must occur in a particular direction. If you are in a car that is standing still and you press on the gas, the car will begin to move forward with a fixed acceleration. It might accelerate slowly, so the vector may be on the shorter side, but this constant acceleration will cause the velocity to increase at a fixed rate. Let's say an additional meter per second every second. So over 5 seconds, it will reach a velocity of 5 meters per second. Let's say you see a skunk in the middle of the road. It's your most favorite animal, so you slam on the brakes. We can describe this as a deceleration, which is an acceleration in the negative direction. Since you are going from a moderate speed to a standstill in a very short amount of time, this vector will be quite long and pointing back towards the origin. Now we understand distance and displacement, speed and velocity, and acceleration, and we can categorize these as being either scalars or vectors. Before we finish, let's look at a moving object like this marble rolling to a stop, and visualize all 3 of these vectors as the object moves. First, with displacement, this vector will just elongate as the marble rolls, and will span the distance traveled. For velocity, the vector will point forward as the velocity is positive, since it is moving in the forward direction, and the vector will move along with the marble, but it will decrease in magnitude as the marble slows down, until eventually disappearing when the marble comes to a rest, where it has 0 velocity. And then for acceleration, the vector points in the negative direction, since velocity is decreasing or becoming smaller per unit time. But it will be constant in magnitude, since this is a constant deceleration due to friction from the surface it's rolling on. We can view all 3 of these at once, just to drive things home. Make sure you understand the magnitude and direction of each of these vectors at each moment in time. Let's check comprehension.
Okay, we're going to stop right there. 1 second. Okay, so I'm going to go back to my notes. All right, so now you should know what position is, what velocity is, and now today we're going to learn about acceleration. So real fast, I want to write position is basically the location of the object. And we measure that in meters. Okay, and then you have velocity, just how fast the object is going. And we measure that in meters per second. And now today we have acceleration. Okay, so do that. The definition of acceleration is a change in velocity over time. So it's anything that is speeding up, slowing down, or changing directions. I'm sure that you have heard the term acceleration many times in your life. Honestly, with my son being 2.5, I hear it on a lot of the shows that he watches. So even he is starting to learn about acceleration at 2.5. So hopefully in everyday terms, you already know what it is, but we're going to dive deeper into the physics related part of it and kind of see how we can calculate it. But here are some everyday examples. So number 1 says a car is at a stoplight. The light turns green. The car goes from rest, so rest would be 0, to 21 meters per second in 8 seconds. The car had a positive acceleration because its velocity increased as it moved. That's just one example. Another example is a dog sees a squirrel. The dog begins to chase the squirrel. The dog moved from 2 meters per second, he was already running, and then he increased his speed to 6 meters per second in 3 seconds. The dog had a positive acceleration because its velocity increased as it moved. Same as the car, it increased its velocity. Now, the third example, a car is traveling at 20 meters per second already. The driver sees a turtle in the road. The car slows down from 20 meters per second to a stop. Stop would be 0 in 4 seconds. The car now has a negative acceleration or deceleration because its velocity decreased as it moved. Okay, so hopefully those examples make sense to you. And now I'm going to show you the formula for acceleration. All right, so we use A for acceleration, and that is equal to the change in velocity over time, which if you look back at the formula, or the definition, change in velocity over time. So right here, that is exactly the formula that we're going to use. Now this delta means change in. I've talked to you about that a little bit before. That means change in. So we could also say that the acceleration of the object is equal to the final acceleration minus, the final velocity minus the initial velocity over time. And that gets you the real formula that you'd want to use, okay? So A equals VF minus VI over T. So let me go down here and write out what everything means. So these two formulas are the same. This is just saying a change in, and so because it's going from an initial velocity to a final velocity, that is a change in. So here's the formula that you want to use in your word problems. All right, so A stands for acceleration, and we measure that in meters per second squared. VF is final velocity. Velocity is measured in meters per second. VI is initial velocity. We measure that also in meters per second. And then T is time, and we measure that in seconds. Okay, so that's your formula. We'll do more formula work tomorrow. What's today? This is Friday, so Monday with all this, but I just wanted to give you an idea of what acceleration is. You've now seen the formula, and so we'll be doing formula work and word problems with all of this on Monday. Now, if I go back to this first question and work it out, it says that the car is at a stoplight. So I'm going to say that its initial velocity is 0. And then in the light turns green, the car goes from rest to 21. So its final velocity would be 21. And it does that in 8 seconds. So time would be 8. And then say I wanted to find the acceleration of that car. Well, I would say A equals VF minus VI over T. And then I would say that A equals, the final velocity is 21. The initial velocity was 0. And it did it in 8 seconds. So then I would just do 21, excuse me. Hold on one second. 21 divided by 8 is 2.6. So the acceleration of this car is 2.6 meters per second squared. And that's how you would solve for the acceleration of that car.